cup. If I took just this portion right here, that would have some positive area to it, wouldn't it? Yes? And I put it in here and I dump it in there and it's in there now, right? So I've somewhat filled up that cup a little bit. And then I go out a little bit further and I take that and I take just that region. That's going to be another positive number, right? I take that and I dump that in there. Now I'm going to have more in here. If I'm telling you that the red region, the whole thing forever, is 1, then I'm telling you I'm never going to overfill that cup. That doesn't bother you? No? I mean, can't I just keep going out? Every time I go out and take a little bit more, it's going to be a positive number, right? So each time I do this, I'm having positive numbers. Go out a little bit more in between there and there. You can't see the red because it's so small, but there's another positive number, right? It's got to have some area to it. If I keep on doing a positive amount, throw a little bit positive more, right? Just you mean to tell me it's not going to eventually overfill?
I mean, eventually we're adding like fractions of a molecule of water.
Okay, so theoretical wise, forget the molecules, forget evaporation, all that. Okay, so is it like that halfway thing where I walk halfway, do I get there? So yeah, this is exactly pretty much that's happening, all right? This is all, I mean, it should cause a problem. I would hope that most reasonable people, there would be some sort of like confusion in your mind here that you are adding up an infinite number of, you're putting an infinite number of positive things in there, right? And I'm trying to convince you it's not going to eventually overfill. That should bother you, all right? But that's what's going to happen with this particular problem. In other problems, if the function is different, if the integrand is different, it actually does overfill. And it just depends on what we're looking at. Now, I'm going to try and convince you of this with a little bit easier example, that it's possible to have this not overfill. So here's the example. Let's say, forget that for now. Let's stick to our theoretical 1 cup. All right, what would happen if I come in here and I've got this perfect instrument where I can measure out whatever I want? All right, so I have this instrument and I'm going to measure out 1/10 of a cup. So I get 1/10 of a cup exactly and I pour it in there. So I pour in 1/10 of a cup. Then I come in here and I measure out 1/100th of a cup and I pour that in there. That's 1/100th. And then I come measure out 1/1000th of a cup, which is still something, right? Yeah? I pour that in there, 1/1000th. And then I measure out how much? You see the pattern I have here? 1/10,000th. Measure it out, pour it in there, right? Each one of these numbers is a positive number, right? Every single one of these is positive. They're getting smaller, but they're all positive. What happens if I do this forever? It's the same idea as what's happening here, right? I have a positive number, positive number, positive number. I keep pouring them in. Is it going to overfill? Well, this I think is easier to show you it's not going to overfill because we can see it pretty easy if we just convert these to decimals. So 1/10 is 0.1, right? 1/100th is 0.01. 1/1000th is 0.001. 1/10,000th is 0.0001. And if I continue that, fine, I continue that, right? If I start adding these up, what's this plus this? 0.11. Now add this one. 0.111. Next one. 0.1111. And if I do all of them, what do I get? 0.111 forever, right? That's what I would get. That's not 1, right? That is not 1. That's smaller than 1. In fact, it's exactly 1/9. It's exactly 1/9. If you do the old school division on this, like this, and bring in a decimal point and do 9 goes into 10 one time, 9, 1, bring down a 0, 9 goes into 10 one time, 9, subtract, bring down a 0, 9, 1, forever, right? You get 1/9. So if I were to do this with my perfect measuring device forever, I'm going to converge to 1/9. Now, will I ever get there? Not in a true experimental way, right? I can't actually do this infinitely many times. But if I could do it an infinite number of times, it would actually be 1/9. That's where the idea of convergence comes from. We're headed towards one value. That's where we're headed, right? We're not headed to 1, we're not headed to 2, we're not headed to 1/2. We're headed to 1/9. So this is just to try and convince you that it is possible to talk about the area underneath an infinite interval and still get a nice number. All right? Okay, so let's do it. Let's actually see the mechanics behind this problem. I had a student in my other class that was very, very much opposed to what I was saying until I showed him that, and then he was okay with it. But we were talking about how there are some things that become at some point counterintuitive, where your intuition is telling you it should be this way, but the math is proving to you that it's not that way. And we have to trust the math, because the math is usually right, okay? So we don't want to be like, you know, you're not like building a bridge and you go over there and go like, yeah, that'll hold, you know? That should work. Don't trust your intuition. Trust the math, right? Here we go. If we're going to do this improper integral that has an infinite interval, what we want to look at first is, do we have any problems as far as discontinuities? Because type 2, which we're going to do in the next class, we have to pay attention to that. So we may as well start paying attention to it now. Are there any issues with this function? Will this function ever fall apart for us? At 0. At x is 0, right? But what's our interval? We are looking from 1 to infinity, right? So we have no problems. I'm just writing this down so that we know. No problems with discontinuities. Understand how I'm just getting you prepared for type 2 on Tuesday? Because let's say this integral went from like -1 to infinity. Then we would have to consider what's happening at 0 also. But we don't. So no problems with discontinuities, we continue. Now I'm just going to use the definition. The definition of this is to rewrite this as a limit. I'm going to use the variable t. I'm going to let t go where? So I'm going to replace that with t, right? So let's let t go to infinity. And the integral is now 1 to t, 1 over x squared dx. So when you're working these problems on the test, right, make sure you include this limit. Don't just write this down without the limit in front. It's not correct. The limit's going to follow us the whole problem until we actually compute the limit. So now just focus your attention on this and do what we did last class. Just act like this was a and b, right? And what we did last class was we found the antiderivative of this, right? So we say equals limit. See, it's just coming with us. And what is the antiderivative of 1 over x squared? -1 over x. And then we put the bar here, and we put 1 here, and up here we're going to put what? T, right? See, 1 is a number, great. The other one is still a variable, it's t. And we're just going to put t there. The next step is to, again, rewrite the limit. And now, doesn't this thing break into like 2 parentheses, and I'm going to subtract them? Right, that's what I was showing you. I'm going to put a big bracket here to contain my 2 parentheses where I'm going to do my subtraction. So what goes in first? T goes in first. T goes in for x. So this is just going to become -1 over t, right? And then 1 goes in for x. And that goes here. So this is just -1, -1 over 1. Questions? Pretty straightforward so far? Equals, I'm going to continue to write the limit. T goes to infinity. And bracket, and let me just clean this up. Negative 1 over t, I'm not going to touch that. Minus minus 1 is plus 1. So now you're back in Cal 1, and you're basically being asked to compute this limit. What is the limit as t goes to infinity of this expression? 1. So why is it 1? This is headed towards 0, right? Now, is it actually 0? No. But that's what the limit was all about. It's saying, hey, as this approaches this, what does this approach? And fixed numerator, denominator gets huge, fraction gets small. So that goes to 0. 0 plus 1, you're just going to get 1. So it is converging, isn't it? It is converging to 1. So converges to 1. The area below this curve from 1 to infinity is finite, right? It's a finite value. Yep, it's 1. All right, well, let's try another one. If it goes to a number, you should write down converges. Yep, converges to that number. All right, next one, 1 over x. So again, do a check real quick. Do we have any issues with the domain? Do we have any discontinuities? At 0 again? But in our interval, we don't have any issues, right? So we can just leave that up there?
Yeah.
Okay, why don't you try and work this one out a little bit. Let me go fill this up with some water. You see how far you can take that. You try and use the correct notation. All right, did y'all finish? Sorry, it took a little longer than expected. What'd you get? It diverges. It went to infinity. So limit t goes to infinity. I'm going to just make sure that I get this all written down properly here. 1 over t, or 1 over x dx. Go ahead and rewrite the limit again. Antiderivative is ln, absolute value x, evaluated 1 to t. I don't need the absolute value. And the reason I don't need it is because look at the values we're plugging in. They're all positive, right? So but I'm going to leave it there. It's not going to hurt us to have it. So now limit one more time. And then bracket, 2 sets of parentheses. And then we have got natural log of, I'll get rid of it now, t. And then over here, natural log of 1. I'll go one more step. This will be natural log t. And then what is natural log of 1? 0, so that's it. So I'm just trying to figure out what happens to natural log of t as t goes to infinity. And this is what the natural log function looks like, right? Has that vertical asymptote right there. So as I go out this way, the function grows forever. So this thing should go to infinity. And infinity is not a number, right? You can't tell me, oh, sure, just put like an infinite number of cups of butter into that mix, right? I mean, that's not a number. So this is divergent. Paul, what?
Like, okay, Paula Dean.
I've never been in prison. Wasn't she in prison?
No, that was Martha Stewart.
Oh, yeah, okay, never mind.
I was like, you know something that I don't know.
Okay.
Paula Dean.
All right, that's all good? No issues? Okay. You just have to put diverges. Yeah. And, you know, we could do something like this. I didn't show my other class this one, but I mean, just to show you that you can get diverges without infinity. What if we were looking at sine x? Or let's make it cosine x so it's easier to integrate. We don't have any negatives to worry about. If I want to integrate cosine x from 1 to infinity, and you know what, let's make it 0 to infinity because we don't have any discontinuities, right? Then geometrically, it looks like this. This is cosine, right? And if we're asking the areas, we've got this area, then 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 this area, right? It looks like they're going to offset each other, and we're just maybe going to get 0 or something. But when you actually do this, limit t goes to infinity, integral 0 to t, cosine x dx, this is going to be limit t goes to infinity, antiderivative sine x from 0 to infinity, which equals limit t goes to infinity, bracket, parentheses, sine of infinity, and then minus sine of 0, right? Sine of 0 is 0. What's sine of it? Sine of t. Sine of 0 is 0. Now take the limit, let t go to infinity. What's